Thank you. It's great to be here. I'm sorry I haven't caught much of the symposium to date, and I'm not dressed like Steve Jobs. These are my soccer coaching clothes, so I'm going to have to run at 1:50 to go start a Ed Metro League soccer game. I want to talk to you today about the James Webb Space Telescope and give you my perspective on what we hope it will be able to do, and in particular, what its role in discovery will be. This is a NASA, ESA, and Canadian Space Agency supported effort. So if I can click ahead here, there we go. Well, many of you have certainly heard of the Hubble Space Telescope. For a while at NASA, it was most popular because of the beautiful images that it could render. And of course, this is simply a matter of the number of pixels that you have across the object of interest. But Hubble's been a workhorse in the astrophysics community since 1990. It's still going. We just submitted proposals a couple of weeks ago to keep on using it. But even only after a decade, the questions began, what will come next? And as many of you know, it takes a long time to get a space mission from conception on a restaurant napkin to launching into space. Hubble has revolutionized many areas of astronomy and astrophysics, but as I said already, it was wondered what would come next. And at the time these questions were being asked in the mid-90s, the sense was that the higher we could go in redshift, and I'll talk a little bit more about that in a minute, our look back time into the early universe, the farther things are shifted into the infrared part of the spectrum. So to do Hubble-like studies of galaxy formation and evolution, when the universe was only a fraction of its current age, it was clear you needed to go into the 1 to 5 micron regime. 1 to 5 microns is a great place to do astrophysics, but it's just the tip of the iceberg, if you will. On this graph on the far left, you can see the background radiation from ground-based telescopes plotted as you go farther and farther into the infrared from 1 to 10 microns and beyond. And because our Earth is about 280, 90 Kelvin, we have a ferocious infrared background between 1 and 10 microns. The red dots were early projections of what was then called the Next Generation Space Telescope and how low the background would be in space. And so this already suggested that the farther you went into the infrared, your ability to make some measurement at a fixed signal to noise would take orders of magnitude less time in space than it would from the ground. So sensitivity is really the #1 reason to do infrared astrophysics in space, because it's cold and dark. The second thing, as you can see on the top right, is the wavelength coverage. Of course, our atmosphere is transmissive at some wavelengths and not others. And the blue shows the transmission, and the white are the deep absorptions in our Earth's atmosphere where you're basically blocked from doing any measurements. And there are very important molecules in our atmosphere that are doing that absorbing that we would like to study in other astrophysical objects. So it just precludes, looking at water at 6.3 microns. It's impossible to do that from the ground. So there's wavelength coverage, which is unique in the 1 to 25 micron range that you can only do in space and not from the ground. Field of view is another element. We want the highest spatial resolution we can get, the fineness of detail, but we want those fine scale images over as broad of an area on the sky as we can, and space also helps with that. This picture on the lower right is one of our meetings of this ad hoc science working group. There's a younger and lower mass version of me in the very back in the center, taken in this picture in 1999, where we were just defining the characteristics of the instruments that we hoped would eventually become the James Webb Space Telescope. And as some of you know, space missions require lots of meetings in windowless rooms. And this is an example of one shown here on the bottom right. Well, ultimately, these conceptions led to the James Webb Space Telescope. In the early days, as Mark was saying, the technological readiness level, the TRL level for many elements of this telescope, including the lightweight mirrors, including the star shade, sunshade that you see here, these were all very low. They were not at 9, they were below 6. And so it took many years and a lot of money and a lot of time and effort to bring all of the technologies needed up to TRL 9 and ready for launch. And again, this was always conceived of as a partnership between NASA, the Canadian Space Agency, and the European Space Agency, which is a wonderful way to share the burden and the intellectual capital needed to carry off these incredible flagship missions. Well, James Webb is going to L2, the Lagrange point 2 of the Earth-Sun system. There are 5 Lagrange points spread out around the Earth's orbit. L2 is getting pretty crowded. There have been about 5 or 6 missions that are there now. There are about 6 more that are planning to go in the next decade. And you can see it's out not quite 3 times as far away as the moon is from the Earth. James Webb will be a 6.5 meter telescope edge to edge. And while large, it's comparable to current ground-based telescopes. It will primarily use the infrared wavelength regime. In the early days, it was just going to be 1 to 5 microns to study galaxies at high redshift. But from the discovery space I showed you a moment ago, it was very clear and easy for those of us who wanted to push the capabilities out to 28 microns, to really dig into that infrared space that you can't do from the ground. There's a cold side and a hot side, and that's the purpose of that 9-layer sunshade when it's fully deployed. On the cold side, on the other side of the sun, it's going to be about minus 388 Kelvin, about 388 Fahrenheit, 38 Kelvin, if you want a quick translation. And on the hot side, it'll be pretty hot, you know, where the sun is powering the solar panels at about 185 degrees. So big temperature difference from one side to the other. And that's what all 9 of those star shade layers are meant to do. JWST will be folded up like an origami in the cone of this Ariane 5. If you're nervous about that, there have been about 104 successful launches of the Ariane 5, so knock on wood, will be another one of those. There have been just a couple of failures of Ariane 5, but this will be launched from French Guiana, hopefully on October 31st of this year, and folded up into the shroud is that 6.5 meter telescope. Interesting story about it being 6.5 meters. If anybody wants to ask at the end, I can tell you. We started off at 8 meters, and it's an interesting story how it got to be a little bit smaller. I'd like to play this video from Northrop Grumman. So we launch, and here is JWST heading out into space. You may remember from the recent Mars landing that there was 7 minutes of terror. Well, here it's going to be several days of terror, upwards of 4 to 5 weeks. There's a lot that has to go on before JWST gets to L2 and unfurls all of its magnificence. So here we're just, coming up on the moon. Let's get that antenna deployed, and we just keep going. Again, we're firing thrusters for a little mid-course correction. We're at day 3 now, and we just keep going out beyond the moon. It's got a long way to go. So now we're looking at the forward sun shield deployment. And then we'll tip a little bit and hopefully get the rest of it unfurled soon. There's the aft. And it's amazing to think about this all of this going well without anyone being able to service it. This, of course, was a key feature of Hubble, that we were able to send astronauts to replace instruments several times over the mission. Here is the membrane spinning out. This has all been tested, believe it or not, several times. So we are confident, but it will be interesting to make sure that everything goes well. There's that sun shield being deployed with the booms. And all of the layers have to then separate, just so. Look at that. What could go wrong, right? There we go. Get those solar panels. Will be coming soon. Get the radiators out to keep the cold side cold. We need to dump that heat somewhere. The cryocoolers will start up, and then the secondary mirror will flop down just so. So the light will bounce off the primary, go to that secondary, and then go into that black tube back to the ISIM, the Instrument Science Module. The wings of the telescope flap up to complete the origami, and pretty soon we'll be on our way. There it is. We're beginning now our orbit at L2. It's not a stable orbit. You need to oscillate around L2. And there's an example of the kinds of trajectories that will go on and on and on over the 5 to 10 year mission lifetime. Well, it's all been tested, as I said, and this is a great shot of JW going into the Johnson Space Flight Center thermal vac chamber, used for Apollo, the largest thermal vac chamber in the world, where the telescope was cooled down to 50 K and shaken, not stirred. And quite an impressive feat of engineering to get this built and tested, and hopefully soon on a boat down to French Guiana. I mentioned that the project is focused on the infrared, and it has a legacy of the Spitzer Space Telescope in the farther infrared, but also the Hubble Space Telescope in the visible and just peeking out into the 2-micron window. So these are complementary facilities, and over time we've learned a lot. There's this picture of Juno from Juno of Jupiter that Mark was just mentioning. The infrared is great at looking at cool objects like planets, where the bulk of their radiation is coming out at infrared wavelengths because of their cool temperature. It's also great at penetrating dust, because light is scattered more efficiently for small particles at short wavelengths. And so infrared allows us to pierce through dust that could obscure objects otherwise. And as I said before, because of the redshifted nature of light, for objects that are more distant due to the expansion of the universe, going into the red allows us to look at more distant galaxies that are far away, where we're seeing the light at early stages of our universe to understand cosmology and galaxy formation and evolution at early times. Here's a graphic example of this dust penetration. This is a young star-forming region, the Eagle Nebula, the so-called pillars of creation. Here's the blue light in the background are emission lines of gases, hydrogen, oxygen, sulfur, and other lines that are glowing because of the ionizing radiation of massive stars nearby. And as you go into the infrared, you'll see a field full of stars, including penetrating through that gas and dust. And many sites of ongoing star formation are seen in the infrared at the tips of these pillars of gas and dust, which you can only see in silhouette in the visible wavelengths, blocking out those emission lines. But now we see through them, and we're seeing stars forming inside. There are 4 instruments for JWST, main science instruments: the Fine Guidance Sensor / NIRISS, which the University of Michigan astronomy staff is involved in the guaranteed time programs and science team; NIRSpec, which is being built by the European Space Agency; and NIRCam, led at the University of Arizona. And again, U of M has a role in that science team; and MIRI, which is a collaboration between ESA and NASA. So each wavelength is tailored for a different set of science experiments, going from the visible near IR all the way into the mid-infrared out to 28 microns or so. These are these instruments packed into their places within the ISIM, the Integrated Science Instrument Module, and NIRSpec and NIRISS and NIRCam and MIRI. Each of them have different abilities to take pictures with imagers, to disperse light with prisms and gratings and spectrographs for spectroscopy. And the stars with the little holes in them are meant to indicate coronagraphy, where you're blocking out the light from the central star, allowing you to look at faint things near bright things like planets, which is a specialty of many of us here at the University of Michigan. Well, a major science theme, which was not the original conception, but as exoplanets were discovered and the field has exploded, studying transits of planets in front of their host star, where you see the dip of the light as the planet comes in front of the host star, will be a major activity of the James Webb Space Telescope. And in particular, we'll be able to do these transit experiments as a function of wavelength allowing us to discern spectra, absorption spectra in the atmospheres of the planets. And this will allow us to characterize the molecular content of these planets. Professor Ted Bergen will speak later today about how these planets come to be made of what they are made of through the formation process. But with JW, we will be able to pierce into those atmospheres and try to take a molecular inventory, maybe even looking for what could be signs of life in some of the systems. A famous planetary system, TRAPPIST-1, recently discovered a few years ago. A couple of the planets in this system are in the liquid water zone, and we will start the characterization process of these tiny rocky planets around, in this case, a very, very low mass star that is just not quite able to sustain hydrogen burning in its core, so-called brown dwarf. These molecules will tell us a lot about the formation and evolution of these systems. And as I said, we'll look for signs of unusual things. I won't even speculate that you could possibly see life, signs of life. There will also be a huge legacy of JWST in studying star formation and the life cycle of stars in the universe. Brown dwarfs, these failed stars that can't sustain hydrogen in their cores, will be a major topic. We have a program accepted focused specifically on that. Star-forming regions, these clouds of gas and dust in space from which new generations of stars like the sun are forming all the time, will be also a major study area, and we again have programs there. And black holes, particularly in other galaxies, will be a major source of discovery for the James Webb Space Telescope. Again, mentioning that some folks in our department have programs already approved. And I mentioned before, I didn't say Professor Emily Rauscher, where's her name? Didn't see it there. Also has programs already approved on the James Webb Space Telescope. This program was what it was originally conceived for, although its mission has expanded, but it will be able to study galaxies within the first few 100 million years of their formation. And one of the big science questions we hope that it will attack is when the first active galactic nuclei, the first black holes in the first galaxy that formed, lit up the early universe, and when the first massive stars formed that also lit up and started ionizing the universe, and when did the majority of the material in the early universe transform from neutral into ionized medium. This reionization era is a key question that JWST is meant to focus on. It will also do extraordinary studies with its incredible imaging power of gravitational lenses. Mass bends light, and if you have a massive object in the foreground of very distant objects, that light is bent and distorted and shaped around the mass, and we are at the focus of those gravitational lens systems. And so we can study galaxies through this process. And my colleague, Karen Sharon, is an expert in this field and has many programs that she's associated with the James Webb Space Telescope. Here is just an example of that distant galaxy where the light is passing by a massive intermediate object and the light is bent around so that we can receive it at Earth. This tells us a lot about the dark matter in the universe that we couldn't see visibly, but we can see its effects due to the gravitational bending of the light. And it also allows us to peer into galaxies at just a tiny fraction of the life of the universe, really, really far back, which we wouldn't be able to see until the next generation of 30-meter telescopes are built in a decade from now. So this will be a great area for my colleague, Karen Sharon. And just to wrap up, JW is the start of what we hope will be the new revolution of space-based flagships in the next decade and beyond. Of course, the W-FIRST mission, the Nancy Roman Grace Telescope, just recently renamed after Nancy Roman, the Roman Space Telescope, an early pioneer she was in leading NASA in astrophysics and space science, and sometimes called the founder of Hubble. W-FIRST will be launched in the second half of this decade and be a very exciting mission as well. And then there are things under consideration. The Origin Space Telescope, a far infrared submillimeter flagship mission that's being studied by the National Academy of Sciences. A smaller and a larger mission, HabEx and LUVOIR, which are meant to have the capacity of imaging in reflected light Earth-like planets around the very nearest stars. And then someday on the lower left, we hope to have a version of a mid-infrared interferometer so that we could take emission spectra of planets around the very nearest stars and again look for those molecules in emission of signs of life around for Earth-like planets around stars like the sun. So finally, let me just add that we do have a number of educational and research programs that folks on this symposium might be interested in. Please check us out, our department in LSA, but it's the astronomy department. And we have a lot of interdisciplinary educational opportunities, and many students from Engine do get joint degrees with us in astronomy. So if you're interested, please check us out. And I'd be very happy to answer any questions. I'll be back on the Slack channel later today in case there are questions that I can't answer now. Thank you very much.
Thank you so much for that great talk. That was honestly really cool. Telescopes have been a interest of mine. I like the work that they do and what they can tell us about the universe. It's honestly quite astonishing. Does anyone have any questions before he has to run? If not, I will go ahead and ask my own then. What discovery or measurements in general are you most excited to hear back from this telescope?
Well, so members of our department are involved in the science teams and early in the design for 2 of these instruments. And so we have a number of pre-approved guaranteed time observations. That's kind of why we do it, right? We want to glean the data after the missions are launched. And I'm particularly excited about a program we have to image planets as small in mass as Uranus and Neptune around a handful of the very nearest and youngest low mass stars. And this is a program we have for the NIRCam instrument, the workhorse camera for JWST. And if there are planets like Uranus and Neptune beyond about 15 astronomical units in the circumstellar environments of nearby young stars, we will see them. We simply don't know how common they are out there. I mean, we have Uranus and Neptune out between 20 and 30 AU. And if they're common, we could get lucky and get a detection. And that would be really remarkable to get the first image of what I would call an ice giant around another star. That would be quite remarkable. On our way to imaging Earths in the next decade with ground-based 30-meter telescopes. But this will be a major milestone in walking towards that goal.
Awesome. That's actually really exciting to me. Will any of this information be available to the public, or will it be held for some time?
Well, so there are varying proprietary periods for the data, but of course, even many of the data will be public instantly and available for download through, the JWST data server at MAST, the mission archive at the Space Telescope Science Institute. However, it might not be very impressive to just pull up FITS images, which is a standard image processing format, and just display them in some, file viewer that you have. But as the results first come in, you will start to see archives of processed images, multicolor images that will be made available as soon as humanly possible through the Space Telescope Science Institute webpage. And that is really the main goal, is to get images out into people's hands as soon as possible.
Hi, Professor Meyer. I have a question. So I don't have much of an astronomical background, so I was wondering if you could elaborate on why the James Webb Space Telescope is going to be at Lagrange point L2, as opposed to, somewhere like on the ground or near Earth where we could access it if something went wrong.
Great question. Hubble was famously in a rather low orbit, and it was relatively easy to access. For astronomers, this was a bit of a nightmare It passed through these particle belts every orbit, every 90 minutes. And there were times when you simply couldn't use Hubble when it was passing through. And then the instruments would need special recalibration when it reemerged. So getting sort of farther away from the Earth is a good thing. And if you're working in thermal wavelengths in the infrared, you want to be as far as possible from any other source of radiation. The moon, for example, would obliterate our detectors if we were accidentally to look at it. So that sunshade is meant to keep out everything. The sun, we need it for power, but it's too bright. We got a shade from that. We're also shading the Earth and the moon as well. And we always want that telescope to be looking out away from the Earth-Sun system, so that we don't have to deal with the background radiation of the Earth itself.
Okay, that makes sense. Thank you. And are there other locations in our solar system that are like more significant where we could send future telescopes? Or
well, we have a dream of this Earth finding telescope I showed, the interferometric array in space. Well, how wonderful would it be to have that out at 5 AU? That would be fantastic. It's colder, as Mark mentioned, and it's fainter. You know, everything that you're worried about is fainter out there. However, it's very, very expensive to get out there. And so this is really the limit. You try to make a balance between cost and risk and schedule versus accessibility, but still getting as far away from the Earth-Sun system as you can. So yes, it would be wonderful to have telescopes out at 5 AU, but very, very expensive, risky, and it'd take a long time.
Right. All right. Thank you.
We also have, if you have time, and feel free, I know it's only 2 minutes, we can maybe field it in the Slack if you'd prefer.
That would be great. I do have to
Okay.
run, but it was wonderful to interact with you all. And I will be back on the Slack channel in a couple of hours.
Great. Thank you so much for your talk.
Thank you. Have a great day.
You too.